All right, welcome to our third unit. We are going to begin ionic compounds and how ionic compounds bond together. But first we're going to just kind of start with an overview a little bit about bonding and some of the rules that we need to know so that we know when elements will bond and when they don't. One of the first things that we need to remind ourselves of would be valence electrons. And valence electrons are something that we've seen before. This is where we're looking at the electrons in the highest energy level, not the highest orbital, but in the whole energy level. And the number of valence electrons is unique for each family, so it helps determine our chemical properties. So certain elements will bond with others because of the valence electrons that they can give or take or share. Some examples: if you look at beryllium, beryllium is atomic number 4, so that means it has 4 electrons. And here we have 1s2 and 2s2, so there's our 4 electrons. The highest energy level that we're using is the second energy level, which only contains just these 2 electrons here. And so the valence number for beryllium is 2. And the valence number for everything in that beryllium family, which would be magnesium and calcium and so on, is also 2. Now if we go to the other side of our periodic table and we look at a nonmetal like phosphorus, for instance, it is atomic number 15. So if we do its electron configuration, we end up with the 1s2, 2s2, 2p6, 3s2, 3p3. In this case, the third energy level is the highest energy level that's being used, which is 5 total electrons, and so phosphorus has 5 valence electrons. Now when we know the number of valence electrons, that will help us create this electron dot structure, sometimes called a dot diagram. And this just is going to be a picture of the symbol for the element. Remember that if it's a 2-letter symbol, the second one's always lowercase, and you just put the number of dots around it representing the valence electrons. So we said that beryllium had 2, so we put 2 dots around beryllium. We said phosphorus had 5, so you would put 5 dots around phosphorus. Now, I personally don't care where you put your dots. I wouldn't put them like all in a row across the top. I would kind of surround the element with the dots, but I don't care if you put 1 on the top, 1 on the bottom, or 2 on the side, or wherever, as long as you have the right amount. There is a rule that we definitely are going to have in this chapter, and this is an important rule because this is how we know when a compound is stable, and that is when it has met the octet rule. So when elements form a compound, when 2 elements have bonded together, we want the atom to be like a noble gas. Remember, noble gases don't react, they're inert, and that's because their electron configurations have full s and p sublevels, and they are they're happy with that. And so that's our octet rule. If you think of s and p, that adds up to 8, and octet is referring to 8. So we want to have 8 electrons. On your periodic table, if you find 1a, 2a, 3a, and 4a, so that's the family that has hydrogen at the top, beryllium, boron, and carbon, those are all mainly metals. Boron is a metalloid, carbon's a nonmetal, but all the other elements in their families are metals. They're going to lose electrons. That's just generally what they do in order to meet this octet rule. And in general, things in 5a, 6a, and 7a, which would be nitrogen, oxygen, and the halogens, fluorine, and everything in their families, mainly we get more nonmetals there than metals, and so those are going to gain electrons. The elements in those families will gain electrons. Now your metallic elements, remember metals make up the majority of our periodic table, the metallic elements are going to lose, and they want to lose so that they can be an octet, have a full s and p sublevel. So if we take a look at sodium, sodium is a metal, it has 11 electrons, So we have our 2, 3, 4, 6 makes 10, and 11. So this is our electron configuration for sodium. But it's an unstable electron configuration because the last energy level that we have here isn't completely full. So what's going to happen is that sodium is going to lose an electron. So when it loses an electron, this electron here in the 3s1 will go to some other element, and that means that now this is the new electron configuration for sodium that has a positive 1 charge because it lost 1 electron. This would be the new electron configuration, which is exactly what the electron configuration for neon is. So again, we're trying to be like a noble gas because the noble gases are stable. And then we have, and there's our octet, octet meaning 8. So here's our 6 and our 2. So we have 8 electrons in that second energy level to make sodium stable. Now, the naming of a cation, remember cations are positively charged. So whenever we name a cation, it's going to be the name that's off the periodic table. So if we say that we have the sodium cation, it's just called sodium. So not very hard there. It's the negative one that we'll have to adjust the naming on. Some things to put on your periodic table. You need to have these charges written across the top because we're going to be using these in bonding about every single day for the rest of the trimester. So these are really important. So anything in the 1A column, going to have a +1 charge. That's hydrogen, lithium, sodium, potassium, so on. 2A is the column that starts with beryllium at the top, magnesium, calcium underneath it. Those are all going to lose 2 electrons, so they have a +2 charge. Now, if we look at our non-metallic elements, which over on our right-hand side are nonmetals, they normally will gain electrons or they will share. So we have some ionic, sometimes we will have covalent bonds with those. And if we look at oxygen, which is definitely on that nonmetals side, this is the electron configuration for oxygen. It has 8 electrons. We have 4, 5, 6, 7, 8. Notice that its second energy level is not full. It only has 6 in there. 8 is what we need for the octet rule. So for oxygen, it is so close to 8. It's at 6 already. So if it can gain 2 more electrons, then it would be like neon, and it would have the 8 in the second energy level, just like neon does. And so oxygen will tend to gain electrons instead of lose, so that we can get that octet rule that we mentioned on the previous slide. So when we name an anion, anions are things that are negatively charged. They are going to end with the suffix, IDE. So normally we say O is oxygen, but when we are talking about the ion has to have the charge, then we don't call it the oxygen ion, we call it oxide. So we take off the ending of the element and we just add that IDE. That comes with practice. We will practice many, many names so that you get the feeling for what part of the word do you take off to add the IDE. To kind of finish this off, you do need to make sure you're putting these on the tops of your periodic table. Anything in the 5A column is going to have a -3 charge, so that would be your nitrogen family through phosphorus, everything underneath it. 6A is the family that has oxygen in it, which we just looked at that -2 because it wants to gain 2 electrons. And then the 7A column would be the halogens, fluorine, chlorine, bromine. Those all want to gain 1. There are 3 forms of bonds that we're going to look at in this chapter, this unit. And I'm going to go through them kind of quickly because we will talk about each one separately. But ionic is when we transfer at least 1 electron from one atom to another. So in other words, 1 gains and 1 loses, and that forms this attraction between the 2. We have covalent, and covalent is where they're going to be sharing the valence electrons. And then we have metallic, and metallic bonds are what hold metals together. Now, the type of bond that we have, whether it's ionic, covalent, or that's actually 2 types of covalent, we can determine this by an electronegativity chart. So we looked at electronegativity at the very end of our periodic table notes. I said we're going to come back to it again. So here is this picture again. Notice inside the box there's a number that is representing the how electronegative. So in other words, does it want to hold on to the electrons or does it want to lose the electrons? So that's what those numbers are representing. And if we just look at the difference in the electronegativities, difference means you have to subtract them. If it ends up being 1.7 to 4, then it's an ionic bond. If it's anywhere from 0.3 to 1.7, it's polar covalent, and then 0 to 0.3 is nonpolar. Now covalent is another unit we'll get to after ionic, so we're just really going to be looking at ionic bondings in this unit. Let's take a look at sodium chloride, NaCl. And if we look at sodium, it was 0.8 and chlorine was 3.0, and that's on the previous slide for the electronegativities. And when you subtract those, you get a difference of 2.2. And so by our little rule thingy up here, 1.7 to 4 is a ionic bond and 2.2 falls in there. So that's one way that we can tell what type of bond we have. Alright, so for ionic compounds, a compound, again, we know this from previous unit, has at least 2 or more elements that are bonded together, and they're going to be made up of cations, which are positive, anions, which are negative. The metal is the cation, the nonmetal is the anion. So if we take a look at the sodium chloride example that we had on the previous screen, here's our metal. We said that the metal was positive, so there's our cation, and then chlorine is the anion because it forms a negative charge. Ionic compounds are going to be neutral. In other words, when sodium gives up an electron and chlorine takes the electron, that causes both of them to have an octet, and so they will be neutral. An ionic bond is then the force that actually holds the plus and the minus charged element together. So the bond is that force that's holding them together because of the give and take of electrons. And so if we take a look at sodium with its 1 valence electron and chlorine with its 7, you can see that sodium does not have an octet. It has that S1, so it has this 1 electron that we mentioned earlier it wants to get rid of. And chlorine has 7 in the third energy level, 5, 6, and 7. And so if it had 1 more, it would be at an octet of 8. So what's going to happen is sodium is going to give up this electron, and it's going to go over here to chlorine. So now chlorine will have the 3s2, 3p6, which again, there's the octet for chlorine. And since sodium is losing, we now have in the second energy level the 6 and the 2. So we have our octet for sodium because now it has 8. So by 1 giving and 1 taking electrons, it actually helps both of them to be stable. Now for chemical formulas, we've seen these a lot, like water, H2O. It just tells us the kinds of elements that we have and how many of each element we have. So for H2O, we know that we have hydrogen and oxygen, but that too also gives us an amount how many hydrogens we have in this case. Ionic compounds are actually a collection of positive and negative ions, and they repeat in a pattern. So for instance, this is what sodium chlorine would look like. It's not really 1 sodium and 1 chlorine. It actually just means that you have 1 sodium for every 1 chlorine, and they repeat over and over, back and forth. It's 3-dimensional, just like this one. So how do we get just 1 sodium and 1 chlorine, since we actually have, like 75 chlorines and 75 sodiums? That is actually the formula unit. We call it the chemical formula, but in ionic compounds it's really a formula unit. It just tells us the lowest whole number ratio that we would have. So in this case, since it's always 1 sodium for every 1 chlorine, the formula unit is the NaCl. For instance, with magnesium chloride, MgCl2, you have 1 magnesium, but you always have 2 chlorines around it. So the crystal would look a little bit different than the previous picture that we looked at. And we will stop with properties, and we will actually pick that up in the next video.